Hi everyone, good morning, and thank you for joining us today on this talk. This talk is about Hardness result for a planar graph and a new algorithm for the Sparsest cut problem in planar graph. And this is a joint work with Amir Aboud and Philip Klein. So the uniform sparse, I'm going to talk about the uniform Sparsest cut problem, and the uniform Sparsest cut problem is defined as follows. So the input is an edge-weighted graph, okay? And the output is a set of vertices that minimizes the following objective function, which is that you pay for each edge in the cut that has one endpoint in U, one endpoint outside of U, and you divide by the product of the two sides, okay, of U and the rest of the vertices. And this is a very classic optimization problem that has received a lot of attention through the years. And even for the planar setting, there has been a lot of work on that because for two main reasons. One of them is that the uniform Sparsest cut is in fact used as a subroutine in various algorithms. For example, the multi-weight cut algorithm approximation scheme from 2012. And it also, originally the motivation was also to use this as a tool to do image segmentation, where the image is seen as a planar graph grid, basically. Okay. So since the problem has received a lot of attention, let me give a brief history. So in general graph, there's a very long history of this, and I'm just going to cite the latest results, which is this Aura-Rao-Basirani algorithm from 2009, which gets you a square root log n approximation and which can be done in n squared time. For planar graph, it's very interesting because this problem is in fact polynomial time solvable. And there is an algorithm by Park and Phillips from the early 90s, which gets you an exact solution in n cubed time. The year before, Rao showed that one can get a constant factor approximation in n squared time, so a bit faster, and in fact a log n approximation in near linear time. But the frustrating thing here is that there has been no improvement on these problems since the early 90s. And so in this paper, I tried to get some progress on that, motivated by the power of planarity, right? Because as many of you know, the problems are usually easier on planar input for approximation algorithm, of course, but also for exact algorithm. You can solve the max flow problem in near linear time. You can solve the diameter problem in subquadratic time. Whereas for general graph, we don't know how to do that. And so, can we use the power of planarity to solve the uniform Sparsest cut in n squared time, in little of n squared time in planar graph? And that's the problem we want to look at today. Our results are as follows. So we show that if you want to get a constant factor approximation, you can in fact do it in near linear time. So improving over upon the n squared algorithm by Rao. And if you want an exact algorithm, you can get a small improvement over Park and Phillips by improving the n cube running time to n to the 2.5. And this is partly due to Craig Fox. And in fact, there is a lower bound of n squared if you believe the mean plus convolution conjecture. So this seems to be a problem for which we won't be able to use the power of planarity as much as we would like and get near linear time. Of course, we use the power of planarity to get polytime exact algorithm, but this is a problem for which we won't be able to get down to subquadratic time even in planar inputs. So in the rest of this talk, I will first give you an insight on the problem, the structure of the problem, then show you the lower bound, and then Philip Klein will give you the approximation algorithm ideas. So a very useful insight when you work on planar uniform Sparsest cut is the one given by Rao in the early 90s, which is that the optimal solution is a single cycle in the dual graph. So if you look at this graph and you believe that the solution, so here I'm seeing the solution as a set of edges that splits two sets of vertices. This connects two sets of vertices. And here you can see a solution in red as a set of edges splitting the graph in the middle made of 6 vertices to the graph to the cycle on the outside. And this the solution here in red, you know that it should be a simple cycle in the dual graph. So what does that mean? That means that if you draw the dual graph, so you put vertices for each face, and you put an edge between two vertices if they are faces are adjacent, then the optimal solution corresponds to the set of edges you put in the optimal primal solution corresponds to a cycle in the dual graph. Okay, and this cycle has to be simple, and so non-intersecting, for example. Okay, and of course, this is a very useful tool because now we can try to change the problem a little bit. And what we want to do is find a simple cycle in the dual graph. Okay, we can somewhat forget a little bit about the primal graph, and we can work in the dual graph. And we can find, we can try to find a cycle in the dual such that what you want to do is minimize the length. And here the length is the length of the edges on the cycle, whose weight corresponds to the primal edge, associated primal edge. And you divide by the number of faces inside times the number of faces outside, because you are working with the dual, so the number of faces inside is the number of vertices inside, the number of faces outside, the number of vertices outside. Okay, so you're basically looking for a Jordan curve in the plane that encloses some number of vertices, and you want to minimize the number of vertices enclosed, and the number of vertices non-enclosed, times the number of vertices non-enclosed, and the length of the Jordan curve. So that's the main problem. And this is very useful, as we'll see, a very useful tool to know that the solution has such a nice and simple structure. Okay, so let me dive into the lower bound right now. So we will use this min plus convolution problem to give a lower bound. This min plus convolution problem is defined as follows. Given 3 sequences of positive integers, A, with A1 up to AN, B, B1 up to BN, and C, C1 up to Cn, you want to be sure that for all k in n, that there is no pair ij such that, so ij are indices such that I plus j equals k, and ai plus bj less than ck. So in the example below, if you take I equals 1, b equals 1, then C2 has to be less than 5 plus 7, which is the case. But on the other hand, if you look at I equals 3, j equals 20, so then you are summing A3 plus B20, that's 16. That's smaller than C23, which is 17. And so that then you should, in this instance, you should output that there is a pair ij, there's a triple ij k that doesn't satisfy the constraint. Okay. And the conjecture is that there is no subquadratic algorithm for this. Okay, so let me dive in now into the reduction. So the primal graph of a reduction is the following one. We have U and V that are connected to U1, U2 to UM, U is connected to U1 to U2 to UM, and V is connected to V1, V2 to Vm prime. And they're connected with dashed edges that are of extremely large weight. So we can make sure that this weight is large enough so that opt is not using any of these edges. So U and V are vertices of very large weight. Now we have this path between U and V, path VA1 to VAN, VB1 to VBN, VC1 to VCN, connecting U to V. And we set the edge VAI to VAI plus 1 of weight AI plus beta, where beta is a very large number. And we do the same thing for B edges, which means that BI to VBI plus 1 has weight BI plus beta. And setting beta to be very large is giving us that for the optimum solution, picking VAI V to VAI plus 1 versus VAJ to VAJ plus 1 is not very different in cost. I mean, it's of course one may have a smaller cost than the other, but the dominant term here is the beta. So it's not the most important thing. The edges VCI to VCI plus 1 have weight beta, again, this very large number, plus t minus ci, where t is the sum of the c's. Okay, so it's just like the complement of ci with respect to c, the c values. Okay, so what does that give us? The first property we have is that an optimal solution must put in different components, different connected components, different sides of the cycle in the dual. The vertices u1 to un, they should be on one side, vertices v1 to vn should be on the other side. And that's because these vertices have very large weight, because of n and n prime are very large numbers, polynomial in n, of course, but very large, such that if you put them in the same connected component, then the denominator of the objective function, which is, remember, the product of the number of vertices inside times the number of vertices outside, would be too unbalanced. Because you want to minimize this objective function, you want to make this denominator roughly balanced, like the two sides roughly balanced. And so if you were not to separate u from v, then you would have something very unbalanced. So we never do such a thing. Okay. So that's the first property. We know that the simple cycle we are looking for in the dual, or this Jordan curve in peak here in this drawing, has to have u in the inside and v in the outside. Okay. This is the first property. The second property is that balance is really important. What I just said is in fact much important than is a much harder constraint than what I just phrased now. We have that if the solution picks the vertices, the edge vi to vi plus 1 and the edge vbj to vbj plus 1, then it is always better to pick the edge vcj plus I to vcj plus I plus 1. And that's because of the way we set m and m prime. If we do such a thing, then you have a denominator that is perfectly balanced. The number of vertices inside will be equal to the number of vertices outside. And that's really important. And remember that because beta is it's what's governing the cost of an edge, the most dominant term, it's the dominant part of the cost of an edge, then it's not very different between vcj plus I plus 1 to vck, for example, vck plus 1. Okay, so it's not very different in cost, but for the denominator, it really matters because then you have something which is perfectly balanced. So this enforces that this beta enforces that you need to really take care of the denominator so that it's really balanced. Okay. So that's the second property, which is really useful because, as you are seeing right now, we are forcing some edges that follow some pattern. bi plus 1, vbj to vbj plus 1, match vcj plus I, vcj plus I plus 1. Okay, so the weight of the edges in an optimal solution have to follow the following pattern. You have some ai plus some pj plus some t minus ci plus j, which is the weight of the edges we have picked so far. And plus the 3 beta are always there because you pay 1 beta for each. And so this is smaller than the weight of the edges in an optimal solution is going to be smaller than the 3 beta plus t if and only if there exists ai, bj, and ci plus j, such that ai plus bj is smaller than ci plus j, which is exactly what we want to detect in the min plus convolution problem. Okay. So in fact, here, what we are forcing is that the optimum solution, we have a denominator that is perfectly balanced and a numerator, which is 3 beta plus t, if and only if you have something that is, the min plus convolution has some triple that is violating the constraint. Okay, so then, as you can see, the min plus convolution has a direct connection to uniform sparsest cuts in planar graph, and so solving uniform sparsest cuts in planar graph is going to be harder unless you can solve this min plus convolution problem in little of n squared time. Okay, so that's the main theorem of this. That's one of the main theorem of this paper, and the second part of this talk is going to be about showing that one can use planarity to still get a constant factor approximation in subquadratic time, and give slightly more structural insight on the problem.
Now I'll describe some of the ideas underlying the constant factor approximation algorithm for MiniQuotient Cut, which is closely related to Sparsest cut. Before giving the first idea, I want to give a little terminology. Each edge corresponds to two darts, one in each orientation. The first idea is a transfer function. Given an undirected planar graph with face weights and a spanning tree T, the goal is to find weights, assign weights to darts so that for any cycle C, the weight enclosed by the cycle C equals the sum of the weights of the darts going around C clockwise. In addition, the darts of T have zero weight. Here's another bit of terminology. For an edge E not in a spanning tree T, the fundamental cycle of E is the cycle formed by using E together with the path in T between its endpoints. So for this edge, here's the fundamental cycle. Now here's the method for computing a transfer function. For each non-tree edge E, compute the weight enclosed by the fundamental cycle of E and assign that weight to the dart of E that's oriented clockwise with respect to the spanning tree. So here's a spanning tree in a graph with face weights. And here's a dart that's oriented in a clockwise direction. Its weight is assigned to be the sum of weights of all the faces enclosed by the corresponding fundamental cycle. And similarly for each of the other non-tree edges. Now, for the edges that are oriented in the opposite direction, counterclockwise, you assign the negative weight. And this has the property that for any simple cycle C, the sum of weights of the darts going clockwise around C equals the sum of the weights of the faces enclosed. Now let's pretend we're trying to minimize the ratio of cost of a cycle divided by the weight enclosed by the cycle. This is equivalent to computing the minimum lambda such that there is a cycle C for which the cost of C minus lambda times the weight enclosed by C is 0. Here's a strategy for computing such a lambda and a corresponding cycle C. Define the cost of a cycle C with respect to a value of lambda to be the original cost of C minus lambda times the weight enclosed by C. And look for the supremum of all the values of lambda for which there exists a cycle such that the cost of the cycle with respect to lambda is negative. And find the supremum and the corresponding cycle C. To carry this out requires testing whether a given lambda is in this set. We use the transfer function to turn that into the question of finding a negative cost cycle. And this is a problem that can be solved in nearly linear time for directed planar graphs. Now I said we were pretending to optimize the ratio cost of a cycle divided by the weight enclosed by that cycle. But the objective function in minimum quotient cut is somewhat different. It's the ratio of the cost of the cycle to whichever is smaller, the weight enclosed by the cycle and the weight not enclosed by the cycle. And the risk of focusing on that first ratio is that our algorithm might find a cycle such that the weight not enclosed is tiny. For example, here is a cycle that encloses all the faces except for the infinite face. So to hedge against that risk, we introduce the following definition. Say a dart D is heavy if the weight of the dart is at least 15% of the total weight. Here are the heavy darts for this example. The algorithm will consider as a candidate cycle the fundamental cycle of each heavy dart. So here are the fundamental cycles of the heavy darts. In addition, the algorithm will consider the graph obtained by deleting all those heavy darts, and then we'll try optimizing that first ratio, the cost of C divided by the weight enclosed by C, to get some cycle that minimizes it. But the algorithm will proceed to iteratively find other cycles by reducing the weight enclosed by this cycle. Okay, so we reduce the weight slightly, reduce the weight slightly, again and again, such that each time weight is removed, the amount of weight removed is at most 15% of the total weight. And I'll explain a little bit more about how that works. Assume T is the shortest path tree with root S. Let's say we use the method described to find a cycle. Now let's assume for now that that cycle goes through S, the root of the shortest path tree. We can interpret the cycle as a path starting and ending at the root S. The iterative algorithm for reducing the weight enclosed by the cycle is as follows. Repeatedly find the last positive weight dart in that path. Let xy be that last positive weight path. We're going to shortcut xy. Let u be the closest ancestor of x in this tree that happens to lie in the suffix of the path starting at y. We replace the dart xy and that suffix with the path in the tree from x directly to u. So that reduces the amount of weight enclosed by that cycle. And again, and again. Each iteration reduces the enclosed weight by at most 15% of the total weight because this graph doesn't have any heavy darts. Also, because it uses a shortest path tree, each iteration does not increase the weight, increase the cost of the cycle. Now, there's a disadvantage to deleting the heavy darts, that the cycle we're looking for, the optimal cycle, might actually use a heavy dart. So we have to hedge against that. So consider this algorithm. The algorithm considers the cycles found in the, using this iterative weight reduction. It also considers all the fundamental cycles of the heavy darts, and it returns whichever of all those cycles has the best ratio. Now, Rao showed that essentially this algorithm is a 3.5 approximation algorithm for minimum quotient cut. We have to go back and look at these assumptions. How do we justify these assumptions? Here's one way. Let S be in turn each of the nodes of the graph and construct the shortest path tree rooted at S for each of those nodes. And Rao used essentially this algorithm to achieve a 3.5 approximation algorithm for min quotient cut that ran in quadratic time. It runs in quadratic time because this process, essentially quadratic time. And it runs in that period of time because it runs in essentially quadratic time because it has to, and it runs in essentially quadratic time. A potentially more efficient method is to modify the weight reduction technique described earlier to work when S is not necessarily on C, but is close to C, in conjunction with a sparse graph decomposition. And Rao used essentially this method to give a factor k approximation that runs in approximately n to the 1 plus 1 over k time, where k is a parameter. So if k is order log n, then this is a nearly linear time algorithm that achieves an order log n approximation. In this paper, we use a better decomposition technique, one that exploits planarity. And as a result, we get a 4.5 approximation algorithm that runs in nearly linear time. Now, in the paper, we claim to get an even better approximation ratio, but that's an error. I apologize for that. Now, I'll say a little bit about the graph decomposition techniques that we use. It's a combination of two decompositions. So let's start with the shortest path tree in the graph. The first decomposition is based on shortest path separators. A shortest path separator is a fundamental cycle with respect to a spanning tree that's a shortest path tree. Therefore, a shortest path separator consists of two shortest paths, two paths in the tree. So the first decomposition is obtained by using shortest path separators to recursively decompose the graph, ending at graphs of constant size. The second decomposition is obtained by just splitting the graph up at distance d from the root, 2d, 3d, and so on, where d is a parameter. This is one decomposition. We have to use several of them to achieve our goals here. But now, the decomposition we really want to use is obtained by combining combining the shortest path separator decomposition with one of these distance decompositions to get a refined decomposition. Each part in the refined decomposition is the intersection of a part from the shortest path separator decomposition with a part from the distance decomposition. Now, let's say we're looking for some optimal cycle C. It lies in one part of the refined decomposition. Now, either that part is a leaf or it intersects the separators used to obtain the next level of decomposition in the shortest path decomposition. The algorithm also, for each part of the refined decomposition, selects an epsilon d net of the vertices making up the separators for the next level. It designates these vertices as portals. As a consequence, each non-leaf part has order 1 portals, and at least one of them is near to the target cycle, for which that part is the smallest part that contains that cycle. And the algorithm uses each of those portals in turn as S in the method described earlier. That's all I'll say about the algorithm. I want to finish with open questions. The first question is, can we find an exact solution to Sparsest cut or MiniQuotient cut in quadratic time? Next, can we find a 1 plus epsilon approximate solution in subquadratic time? And finally, can we get a fast polynomial time approximation algorithm for bisection? So a polynomial time bicriteria approximation algorithm is known for planar graphs, but the degree of the polynomial depends on epsilon. Okay, thanks for your attention.